Welcome to the sixth lecture in our series on quantum mechanics. In the previous two lectures, we discussed the mathematical foundations of quantum mechanics. In this lecture also, we will continue to understand the mathematics of quantum mechanics. So this will be the third part of our sub-series in which we discuss the mathematics related to quantum mechanics. This is the plan for our lecture today. We will first talk about the Hamiltonian operator and energy eigenstates. We will then do some problems related to this concept. After that, we will talk about projection operators and do some problems. And we will end this lecture with a discussion on trace and its properties and do some problems related to trace. The Hamiltonian is a very useful and important concept in physics. In classical physics or classical mechanics, the Hamiltonian is the total energy, kinetic energy plus the potential energy. In quantum mechanics, we have to replace the kinetic energy and the potential energy by their quantum mechanical counterparts. So we have to replace these by quantum mechanical operators. Now, the kinetic energy is given by this, or more generally given by where P is the momentum. So this is the kinetic energy and this is the potential energy. To take it to quantum mechanics, we have to replace the classical momentum with the quantum mechanics momentum operator. So this would become, now the momentum operator, as we have discussed in previous lectures, is given by this. So the kinetic energy operator would be given by this. If we expand it, it would be given by this. So if we expand this del square further, it would be something of this sort. This is our Hamiltonian operator. Now the Hamiltonian operator satisfies this equation, and this equation is central to quantum mechanics and is called the Schrödinger equation. So on the left hand side, we see that the Hamiltonian operator operates on the state ket, and on the right hand side, we see the time derivative of the state ket. So the Hamiltonian is generating the time evolution of the state vector or the state ket. So this is the Schrödinger equation, and solving the Schrödinger equation for various scenarios is what we will study in future lectures. So a lot of quantum mechanics is about solving the Schrödinger equation for various Hamiltonians or for various physical situations. If the Hamiltonian does not explicitly depend on time, then we get this equation. So Hamiltonian operator, this is the eigenvector or eigenstate. Here we have energy. So this is the eigenvalue and this is the eigenvector or eigenstate. Now we can say that this ket is the eigenstate for this energy. So we can call this ket as the energy eigenstate or eigenket or eigenvector corresponding to this energy. To take another example, if we have something of this sort, then we can say psi1 is the energy eigenstate or eigenvector corresponding to energy E1 given the Hamiltonian this. Let's start with this problem. This problem is taken from the book on quantum mechanics by Zitelli. It says a particle has a Hamiltonian. This is this ket an eigenvector of this Hamiltonian. Then we have to check if this Hamiltonian operator is Hermitian or not. And we have to find the energy eigenvalues and eigenvectors of this Hamiltonian operator. Let's start with this part. Is this operator Hermitian or not? Now we have studied in our earlier videos that an operator is Hermitian if the Hermitian adjoint of the operator equal to the operator itself. So let's find the Hermitian adjoint of this operator. To find the Hermitian adjoint, we should keep the diagonal elements the same. The off diagonal elements the rows and columns, they get interchanged, but we have to put the complex conjugate of any number that we find there. So this I will come here and become minus iota. This minus iota will go up here and become iota. Similarly, this 0 and this 0 will interchange positions. Since it does not have a complex part, it stays the way it is. This 1 and this 1 also interchange positions, and this becomes our Hermitian adjoint of this operator. As we can see, this is the same as the original Hamiltonian. So therefore, the Hamiltonian operator is indeed Hermitian. Now let's check if this ket is an eigenvector of our Hamiltonian operator. To do that, we have to check if we can put it in this form. This is the operator, this is the eigenvector or eigenket, and this is the eigenvalue. If we can put our Hamiltonian operator and our ket in this form, then this ket is indeed an eigenvector of our Hamiltonian. If not, then it is not an eigenvector. Let's try it out, and we get, oh, this cannot be put into this form. We cannot take a constant out of this and put this ket here. So since this thing cannot be put into this form, so our eigenvector equation is not satisfied. This means that our lambda ket is not an eigenvector of our Hamiltonian. So now we ask ourselves, what are the eigenvectors of H and what are the corresponding energy eigenvalues? Let's clear this screen a bit to do these calculations. So ultimately we have to find a set of kets such that this is satisfied. These would then be the eigenvectors or eigenkets, and these would be the eigenvalues. And since these are the eigenvalues of the Hamiltonian, these are called the energy eigenvalues. So the way to do this is described in any book on linear algebra, but let's do it here. First, we need to find the eigenvalues. In order to do that, we have to solve what is known as the secular equation. That is, determinant of. When we solve this equation, we will get a set of A's. These A's are the eigenvalues of our Hamiltonian. Since we're talking about the Hamiltonian, so these would be called the energy eigenvalues. Once we have that, then we can find the eigenvectors. So when we find the determinant of this, we get, so this equals 0. The only way this can equal 0 is either A equal to 1 or A equal to or A equal to. So these three A's, we can call them A1, A2, A3, are the eigenvalues of our Hamiltonian. And from these we can find the eigenvectors of our Hamiltonian. Let's start with one of them. Let's use A equal to 1 as our example. So our Hamiltonian multiplied by some eigenvector, let's call it xyz, has to be equal to 1 into that. This is what this is. This is our eigenvector equation. Hamiltonian operating on the eigenvector will yield that same eigenvector with eigenvalue multiplied to it. Our eigenvalue comes here, and this is our eigenvector. When we solve this equation, we get three equations. We have to find some x, y, and z which satisfy these three equations. And we can put x equal to 1, y equal to z equal to. So 1 iota is an eigenvector. So this is an eigenvector corresponding to the eigenvalue A equal to. Similarly, we can find the eigenvectors corresponding to A2, which is 1 plus root 3, and A3 as well. Moving on, let's discuss an important concept. It's called functions of operators. So any function of an operator, we can put it into Taylor expansion. So any function of operator can become the Taylor expansion of something like, which is a function of an operator A, where this is the identity operator. So this is the Taylor expansion of any function of operators. An important thing to realize or to remember is that if A and B are two operators that commute with each other, then any function of A will also commute with B. Similarly, any function of B will also commute with A. And any function of A, therefore, will commute with any function of B. Another important result is that if you find, or if you want to find the Hermitian adjoint of a function of A, you just need to take the conjugate of the function, and instead of A, it becomes a function of the Hermitian adjoint of A. Based on this, let's do another problem. Under what conditions is this operator unitary? Now we know that a unitary operator is such that the Hermitian adjoint of that operator equal to the inverse of that operator. In other words, if you have the Hermitian adjoint of the operator and you multiply it by the operator itself, then since this is unitary, this becomes equal to the identity operator. So this is the way to confirm if U is a unitary operator. So we have to find out under what condition is this unitary equal to the identity operator. But in the previous slide, we had seen that this is a function of operator. In order to find the Hermitian adjoint, we have to do this. One is true because of this theorem. We take the complex conjugate of the function and we replace the operator by its Hermitian adjoint. So that is why we had to substitute iota by minus iota, that is take its complex conjugate and replace this operator with its Hermitian adjoint. Now this has to be equal to I. For this to be I, it should be equal to I. And for this to happen, that is this operator G has to be Hermitian. So if this G is Hermitian, then this whole e raised to power I epsilon G becomes unitary. Next problem is this matrix unitary? So any matrix A will be unitary if the Hermitian adjoint of that matrix multiplied by that matrix itself is equal to, this is one way of doing it. The other way of doing this is to find the inverse of this matrix and to show that that is equal to its Hermitian adjoint. This would involve finding the inverse of this matrix, which can be done, but it's a little bit of a longer calculation. The easier thing is to find the Hermitian adjoint of this matrix multiplied by the matrix itself and see whether it results in an identity matrix or not. So let's find the Hermitian adjoint of this matrix. We keep the diagonal elements the way they are, interchange the rows and columns for every element, and take the complex conjugate of all the elements. So this is the Hermitian adjoint of our matrix. This is the original matrix itself, and we can easily see that when you multiply them together, it is not equal to an identity operator, which should have looked like this is what an identity operator looks like, but this is not equal to the identity operator. So this matrix, since its Hermitian adjoint is not equal to its inverse, so it is not a unitary matrix. Let's now discuss the concept of projection operators. An operator is said to be a projection operator if it is Hermitian and equal to its own square. So the operator P here is a Hermitian operator and P squared is equal to P. So P is a projection operator. Both these conditions, Hermitian and being equal to its own square, need to be satisfied. Another example of projection operator is the identity operator. We will discuss a little bit more about identity operators in the next few slides. Let's now discuss a few properties of projection operators. The product of two commuting projection operators is also a projection operator. Let's say we have two projection operators, A and B. Since A is a projection operator, so A is Hermitian and the square of A equal to A. Similarly, B is a projection operator. Now let's see if the product AB is a projection operator. And we have been told that AB is commuting. That is, A and B commute with each other. That means AB equal to BA. Let's now check if the product AB is a projection. To check that, let's first check if it's Hermitian. So this is what this becomes. Now B is Hermitian, so it becomes B. A is Hermitian, so it becomes equal to A. But B is same as AB, since A and B commute. So the Hermitian adjoint of AB is AB. The product of A and B is Hermitian. Now let's look at the square of AB. We can expand it in this manner. Now since B and A commute, we can write it as, now A square is nothing but A, because A is the projection operator. And by definition, A square should be equal. Similarly, B square should be equal to B. So the square of AB is also equal to AB. So AB, the product of A and B, satisfies both the conditions needed for something to be a projection operator. So we can say that the product of two commuting projection operators is also a projection operator. Two projection operators are said to be orthogonal if the product is 0. So if you have two operators, A and B, and if AB equals to 0, then A and B are said to be orthogonal to each other. The sum of projection operators is a projection operator. The projection operators are mutually orthogonal. So if you have projection operators A and B, and if A and B are orthogonal to each other, that is A multiplied by B gives you 0, then A plus B is also a projection operator. Now let's solve this problem. We have to show that this ket-bra product of psi is a projection operator only if the ket of psi is normalized. Let's now recall the conditions for something to be a projection operator. Let's now examine these conditions one by one. Now this is easy to see. This is the same as, this is indeed Hermitian. Now let's look at the other condition, square it. Now if this is normalized, if the ket of psi is normalized, then this bracket product becomes equal to 1. So then we get, so the only way in which this ket-bra product squared can be equal to ket-bra product is if this equal to 1, which means is normalized. So we have proven that this is the projection operator only if this is normalized. Let's now discuss the concept of trace. The trace of an operator is just the sum of its diagonal elements. Let's expand this thought further. We learned that any operator can be put into a form of a square matrix. And we learned that the elements of this square matrix are given by something like this, in which etc. gets are basis vectors. So if we represent the operator A as a square matrix, where the elements of the matrix are given by this, so we represent A square matrix in this basis vector set, then the trace of A is the sum of the diagonal elements of this matrix. Now, an important thing to note is that the choice of the basis vectors is arbitrary. If we can represent any operator in one set of basis vectors, we can represent the operator in a different set of basis vectors also. So the choice of basis vectors in which to represent an operator is arbitrary. However, the trace does not depend on the orthonormal basis that we use to represent the operator. So whether you represent A in one basis vector set or some other set of basis vectors, the trace does not change. Another property of trace is that if you have trace of A and B, you can expand it as trace of A and plus trace of B. Also, if you have any scalar multiplying A and B here, those just come out as they are. This is another property of trace. Trace is invariant under a cyclic permutation of operators. So if you have trace of A, B, C, let's represent A, B, C in this form. Then whether you go from A to B, B to C, C to A, as long as you go in the same order, the trace remains the same. So let's see, trace of A, B, C is equal to trace of, let's not do B, C, A. Note that we have not changed the way we go through this cycle. Similarly, this is equal to trace of C, A, B. If we were to go in the opposite direction, then it is not equal to these traces. This is not equal to trace of C, B, because here we have gone in the opposite. So The trace is invariant under the cyclic permutation of operators. So you can put the operators in whatever way you want, but they have to maintain the same cyclic order. Another important property is the trace of the Hermitian adjoint of A is a trace of A, the complex conjugate of the trace of A. In an earlier lecture, we have learnt about the identity operator. We learnt that have the inverse of any operator multiplied by that operator, we get the identity operator. Similarly, when the identity operator multiplies by any ket or bra, we get the same ket or bra. The identity operator can be represented by square matrix. In fact, any operator can be represented as a square matrix, but the identity operator, only the diagonal elements are non-zero and they're all equal to 1. Another way of representing the identity operator is something like this, and we can easily check it. Let's say we have this basis. Now the identity operator will be, and you can easily see this when you represent it in this diagonal form. For example, this element is given by, and when you do this, only this part will survive, and you can write it as, which is the, you can see that you represent the identity operator in this form. This is a very useful form for solving problems, and we will see the application of this in the next slide. Here we are required to show that the trace of AB equals the trace of BA, and we have to show that the trace of the commutator is always 0. So the trace of AB can be written as, you can use this format here, in which phi n are the basis vectors. So this is the trace of AB. Now here we can insert our identity operator in the form given by this. Identity operator is, let's say, J. So we can insert it here. This is our identity operator, which we have inserted inside this. We can insert an identity operator wherever we want. So we insert the identity operator here. Now let's bring out this and make it. Now note that these numbers, these quantities are scalars. We can move them around. So we can write it something like, once we do that, we can take this sigma back in the center, an opposite thing to what we did earlier. Now this guy again is nothing but an identity operator, which now we can remove. What we get is, now by definition, this quantity is the trace of, so through these calculations, we have shown that the trace of AB equals the trace of BA. So now to find the trace of the commutator of AB, we have to just do something of the trace of sum of two operators is this trace of the first one plus the trace of the second one. Now we have shown that trace of AB equal to trace of BA. This becomes, so we have proven what we were set out to prove. With this, we end this lecture, in which we continue to explore the mathematical foundations of quantum mechanics. In our next lecture also, we will continue to explore the mathematics needed to understand quantum mechanics. Thank you.